Hello geometry students. Last time we did section 9.2 that was about special right triangles. Today we are going to start section 9.3 that's basically about similar right triangles. Alright, so the right triangles, but they're going to be similar and some theorems based on that. So we're starting from page number 254. So here this is from Big Idea Math Journal, page number 254, and it's section 9.3, which is about similar right triangles. So geometric mean they have already explained on the bottom, so we just want to review. We did similarity in chapter 8, and just to remember what were the theorems we did for similarity. They were, first theorem we did was SAS, where we needed two proportional side and an included congruent angle. Then we did another that was SSS, that was about three proportional sides, and one was AA, where we were just looking for two pairs of congruent angles for the triangles to be similar. So these were the theorems we did for similarity. Now we are going to learn similarity in context of right triangle. So let's move to the very first theorem here. So very first theorem is here, right triangle similarity theorem. So it's the similarity theorem in the context of right triangle. So that says if the altitude is drawn to the hypotenuse of a right triangle, then the two triangles formed, you will see if you draw an altitude, you see two triangles formed are similar to the original triangle and to each other. So it means if you have a right triangle, you can see this is an original right triangle. So let me make that bigger. We see this is an original right triangle, and in this right triangle, if I draw my altitude from C, altitude means drop a perpendicular, that's going to be perpendicular here, that's my altitude. Then the original bigger one and the new two smaller one, this left hand side one and this right hand side one, they're going to be similar to each other. So what they have done, they already shown you these two triangles. They have already drawn it separately here. They have shown it so that it's easier to understand, and they have written the similarity expression on left hand side. So what I'm going to do, I'm going to redraw the original triangle, so you can see that if I try to kind of change the orientation of this triangle, so if I want to redraw the whole original triangle, that should be something like this, because it will be easier for me to see how the statement is written. So in that case, I see the shorter leg and the opposite angle, that's A. So means this should be A, and the point, the vertices where it is right angle, that's C and B. So when I'm comparing my sides, so I'm going to use it in a similar way. I'm just going to redraw the triangles here so that you can easily understand how these similarity expressions are written. So I'm going to first draw this original triangle here. That's the bigger one. And this is ACB. And in that bigger one, you have dropped a perpendicular or you have drawn an altitude, you got these two. But I'm going to redraw it. Again, just imagine you just rotate it. You rotate this triangle, so you get it like this. So it is going to be like this, 90. D is here, and this is A, and this is C. And this is already in the same orientation, because when the orientations are same, it's easier to compare. So I'm just bringing it down here. A, D, C, and this is C, D, B. All right, and these are 90 degrees. So I have drawn the original triangle over here. then these two in the similar orientation so that my comparison is easier. So basically what they're telling you, they're saying that all three triangles, they are similar to each other. They're similar and they have written the expression here. You can say CB and D. So if you go to this one, CBD, that's similar to ABC. So you can say that CBD, the first expression, CBD, this is, so I would name the other triangle, the original one, in the same way, CBD, so it is ABC, it's given here. Now if I pick another one, so if they're taking the ACD, that's going to be again similar to ABC. It's here. So it's the same thing. If you can read it from here or you can draw it separately and you can understand. So that's ABC. And then purpose is that the two different triangles, smaller one, they're individually similar to the original one. So we first said this is similar to this. Then we said these two are similar. Then finally we're going to say that these two are going to be similar. So that's going to be CBD is similar to ACD. So we have three expressions. So if we drop a perpendicular in a right triangle from the point where there is 90-degree angle is formed, then the next two smaller triangles, they're going to be similar to each other as well. They will be similar to the original bigger triangle. That's the right triangle similarity theorem. After that, there is another concept, that's geometric mean. So that's a very basic concept. Here, what you're supposed to understand, if you are supposed to find geometric mean of two positive numbers, A and B, so that is going to be X. And how you can write the expression, the numbers are A and B. These are the numbers here, the one we have taken, and the mean is X, so the mean is here. You can see the numbers A and B here, and the mean is X. So this is kind of proportion. A over X is X over B. You do the cross multiplication. What do you get? So you multiply it. You do the cross multiplication like that. A over X is X over B. Do the cross multiplication like this. X times X, it means X times X is A times B, and X times X is X squared, AB, and we got it here. And then we can take the square root and we get our geometric mean for AB. You can directly use this expression, that is AB. So for example, if I have to find the geometric mean, suppose my two numbers, example, if my two positive numbers are if I say 7 and then 4, and we have to find the geometric mean for that. So you can directly write down the geometric mean will be, you just multiply those two numbers and take the square root. That is going to be 28. But we need to always write down that in radical form. You can always factor it out. You can make a factor tree, or you factor it out any method, whatever method you like. And then I have, that is what? 2 times 7. I have to find the square root. I would pair it up, like as many pairs I can form. So this is way you can take a square root or whatever method you like to do it. So 2 root 7, that's our geometric mean for numbers 7 and 4. Any question, then please let me know. So we, on this page, we did right triangle similarity theorem and geometric mean. Then we have two more theorems. Those are geometric mean but altitude theorem and geometric mean length theorem. Sometimes it's really confusing for students, so I'll just show you how to do it easily. So the very next one is geometric mean altitude theorem. So in this case, what do we see? It is just like a use of geometric mean, but here we are going to find our altitude. All right, so if we have a right triangle, and from in a right triangle, this is the right triangle, the whole original one. If I drop a perpendicular here, I draw an altitude here. So in a right triangle, the altitude form right angle to the hypotenuse, divides the hypotenuse in two segments. So two segments, you see they're talking about here. I'll show you. The length of the altitude is geometric mean of lengths of the two segments of hypotenuse. Now, what does it mean? Basically, they want you to say that if you're finding this measurement, this will be when you drop a perpendicular, then you see there are two segments form of hypotenuse. This is your hypotenuse for your original triangle. And you need to drop a perpendicular from where right angle is formed. So the point where right angle is formed, from there you drop a perpendicular to the hypotenuse and you see two segments are formed. So in that case, you will be saying that if you have to find CD square, CD is actually geometric mean of AD and TB. And what it is, the expression is CD square is AD times PD. If I say geometric mean, it means if you have to find further, you can write CD square root of AD times BD. So we can write it this way also. So both are equivalent no matter which one you use. So we start from this one. And yes, so let me give you an example. What if I take a different picture here? Suppose my triangle is like this. That's my right triangle. According to this theorem, where geometric mean altitude theorem, and I name it PQR, if I drop a perpendicular from the point where the right angle is formed, so my perpendicular is supposed to be from here to the hypotenuse. This is the hypotenuse. I'm going to drop my perpendicular. That's my altitude. And we're finding altitude. That's why the name is geometric mean altitude theorem. So that's going to be, I'm supposed to find this thing. So this is dividing the whole hypotenuse in two equal parts, and those parts are this and this. So in order, for the sake of convenience, let me say this point is PQRS. And if I have to use this theorem, my expression would be what? Can you think about that? Think quickly so I can write down afterwards. All right, I'm going to write. So the altitude QS square equal to PS times SR. PS times SR. So basically you can generalize this formula. You can say altitude square equal to part 1 times part 2, or segment 1, segment 2. And from where are they coming? That we have to keep in mind. They're coming from hypotenuse. All right, I hope you get this. So this is a very important theorem. After this we have another theorem, that's geometric mean leg theorem. Now, what if we are not interested in finding this hypotenuse? If we draw an altitude, this altitude, we draw an altitude, but we are interested in legs. So that's next theorem, that's geometric mean leg theorem. All right, so keep in mind, again, if we want to review what is the leg, just for the sake of kind of review, the sides which make the 90-degree angle, they're called legs, and the one which is opposite to 90, that's called hypotenuse. All right, so we're going to apply this theorem here, and the geometric mean leg theorem, it says here, let's see, what does it say? in right triangle, it's about right triangle. It's the geometric mean leg theorem. The altitude from right angle to the hypotenuse divides hypotenuse in two segments. It is same thing like in our previous theorem. When we drop an altitude, it divides in two equal parts. Then after that, what do we have? The length of each leg of right angle triangle is geometric mean of the length of the hypotenuse and the segment of the hypotenuse that is adjacent to the leg. Let's make it simple. Maybe wording is too much complicated. So in simple words, how can we see that? I'm going to make it bigger. The figure, it means it's the same picture, but it says if you drop a perpendicular, this is your perpendicular, this is a right triangle to the hypotenuse, the perpendicular is to the hypotenuse. If I'm trying to find this CB square, I'm trying to find this leg. This CB square is actually DB. It's what? I have to use that segment which is towards that leg. The segment of the hypotenuse which is towards that leg. DB and times AB. Now I have to take the whole thing. AB, whole hypotenuse. Alright? But if I'm trying to find AC square, if I want to find this one, I'll take the part AC square which is towards this leg, the part segment of the hypotenuse which is towards this leg times the whole hypotenuse. It's just like taking the part of towards that leg times the whole hypotenuse. So we can summarize it. So we can say just in general notation, if I have to find leg, because these are legs, actually these are legs, we're finding that's why it's a leg theorem. If I'm finding leg, so what I have to do, leg square is what? Segment of hypotenuse towards the leg, the part which is towards that leg times hypotenuse, the whole hypotenuse. So whatever it is, just you accordingly change it. So both of them applies to this thing. So I would show you one more example. We think about how to write this thing and we will be done for today's lecture. So I'm going to make it smaller and let's take an example here. If I draw a triangle, suppose I'm just drawing in a different orientation, the same one which we did in previous example. So that's our PQR, that's 90. Let me drop a